Okay, welcome back everyone. In this session, what we're going to talk about is shear stress and how shear stress relates to connecting parts together. As a review, we have covered stress before. So we started that conversation with stress last time talking about forces. We said there's a tensile force or tension that's pulling an object. We said compression is like pushing in on the object, right? We said a shearing force is like, when you think about scissors, like cutting it, or if I'm holding it here and I like karate chop it, I have two forces almost on top of each other that are making this material want to, in essence, break in half right down the center here. We talked about a bending moment or bending force like that, and we talked about a twisting force, which is like a torque. And then from there we said, well, with this idea of stress, and what we looked at was a tensile stress in tension, because it had to do with our lab with the tensile testing machine, right? We said that the idea of stress is a force divided by the cross-sectional area, almost like it's evenly distributed across the cross-section. I didn't really draw this last time, but we could think of the force being distributed all throughout evenly around this cross-sectional area, right? And that's that stress, which we called a sigma. And so we said our basic definition was that stress is just equal to force over area. So all that should be reviewed. We covered it last time. And this time what we're moving on to is the other force of shear. So the first one had to do with tension and compression. Now we're going to move on and look at shear. So of course a shear stress comes from a shear force. And just like last time, what I could do is look what's going on inside my object, my cylinder, whatever this might be. If I were to only draw the right-hand side, then I would only have one of those forces. Now, by the way, we didn't label this before, but a shearing force is labeled as a V, where an axial force we're labeling as an F, right? So what it would mean is all throughout, just like before, all throughout this cross-section, there would be a stress that is resisting this shearing force. Well, I drew that one a little outside, but something like that. And we're going to call the stress parallel to the surface as a shear stress. And if I have to define it, it looks very similar to what we had a second ago. We do have a different Greek letter. That's the Greek letter tau. And we would say tau is equal to the shear force over the sheared area. So before, what we had was our sigma, or axial stress, is the force over the area. Well, this is the same idea. Our shear stress is the force over the area. It's just a shearing force over the cross-sectional area. And this guy here, once again, is a tau. Now, unit-wise, it would be the same units that we had up here. So our units would be either PSI, but more than likely it would be KSI, kips per square inch, and that's in standard units, and megapascals in metric. So let's take a look at an example of how this would work. All right, so in this example, what we're given is that we can have a maximum shear stress of 0.9 kips per square inch in the wood. Now, if I look, what I have is this interlocking member where I have steel pulling one direction, wood pulling the other. And wood is not as strong as steel, so it would probably fail first. And you could look this up in any table that that wood has a shearing strength of 0.9 kips per square inch. What we're trying to find is how much load can I put on here? How much force can I pull with P in order before this would fail, right? So if you want to pause the video and try it on your own, that'd be pretty cool. If not, you can just watch me solve it. So with that in mind, what we really need to do is determine the sheared area, because we talked about the force. Well, force is P. You know, if I write down what I know, my equation was tau is equal to V over A. Well, I already know my tau, that's 0.9, and V, the shearing force, is whatever P is equal to. That's what I'm looking for. And then the question is, what is that cross-sectional area that would be shearing off? And maybe you can envision this, maybe you can't, but it would in essence break right through there, right? So I can imagine that I'd have this piece that's sectioning off. Well, I need to know the dimensions of that piece. It would be this 3 inches in one direction and 0.6 the other. So I have a total cross-sectional area of 3 times 0.6. So the way I would solve this problem, starting with this tau is equal to V over A. Like I said, I know this tau is 0.9 kips per square inch, and I'll write out the units so we can see how they all cancel out, is equal to the shearing force, well that's that, whatever that value P is, over the cross-sectional area, 3 inches times 0.6 inches. So in essence, it's just some algebra at this point, and my inches in these inches would, in essence, cancel out with those inches squared, and I end up with P is 0.9 times 3 times 0.6, which gives me 1.62 kips, or 1,620 pounds, right? All right, so the other topic we need to talk about is how this whole shearing force relates to our connections, like if I have a bolt or a screw or a nail. And so let me start with the title. And a lot of this depends on how the connections are made, meaning the first type of connection we're going to look at is called a single shear or lap shear. So let me draw that out. So this would be an example, and you can see why it's called a lap shear, meaning these two boards are lapped on top of one another, and I have this pin that is going through and connecting. You can imagine it's all the way through here, right? Connecting these two boards together. Well, if I thought about what's going on from that pin's perspective, what I can imagine is it would break into two different pieces, right? So I would end up with a sheared area that is like that. So that would be my stressed area or area under stress. And we said before, if we want to find the area, cross-sectional area, it is of a circle, it's pi r squared. But because we know everything in diameters in construction, like this is a 1/4 inch diameter pin, then I'm going to use pi over 4 times the diameter. In this case, it's a 1/4 inch. And that's what I'm squaring. So if I punch that in my calculator, I ended up with 0.0491 square inches. So if I wanted to know the stress on that pin to make sure it isn't going to fail, I can plug that into the equation. V, or the shearing force over the cross-sectional area. I have a force of 200 pounds. The area is 0.0491. And that gives me something like 4,070, and the units in this case would be pounds per square inch because I'm starting off with pounds. Of course, I could convert that and say it's 4.07 KSI, right? Now, another type of connection would be if instead of I had this lap connection, what if I had it pinched on both sides? So something like, let me draw this out for you. So something like this. So really the only difference between my lap shear and this one is now I have this like this wishbone shape, right? And I'm clamping down on both sides. So if I thought about what's going on with the pin in this case, and I said, well, where would the pin actually fail? Well, now it would have two shear planes where it could fail along. And hopefully you could see that. I'd end up with 3 pieces if this thing failed and broke apart, right? So it would break right at the plane between those two boards, right? Because of that, and because of this, I end up with 2 sheared sections. This is called double shear. So single shear had 1 shear plane, 1 stressed area, and of course double shear, like the name implies, we have these 2 sheared sections or stressed areas, right? So if I wanted to know the shear stress on that pin, and now we're still pulling with the same 200 pounds as I was last time, you might be able to figure it out in your head exactly how much my stress would decrease, but mathematically, let's go ahead and show it. Tau is still equal to my shear force over my area. I still have 200 pounds, but for cross-sectional area, it's the total area under the shear stress. Well, now I have two of those, right? So I have 2 times that cross-sectional area, which we said was pi over 4 times a 1/4 inch squared. Well, I'll put that all in, and I end up with 2035 psi, right? Which is exactly half of what we had before, because I have twice the sheared area. So before we had 4,000, now we're at 2,000. Or if I were to convert it to KSI, which is more common, 2.035 KSI, something like that. And then the last type of connection that we have to consider, or the type of shearing due to a connection we need to consider, has to do with this, where this pin is located. So I can see this pin is going through these 2 boards. What would happen if I put this pin too close to the edge, right? You can imagine that board would break. The pin wouldn't break, but the board would break. And the question here would be, what does it look like when it breaks, or what does that? So let me draw that out. So this type of failure, by the way, is called shear rupture or tear out. And the way I tend to remember that is it's like tearing out a big chunk of material. Now it's kind of hard to see in this 3D drawing. I tried to draw the 2 shearing planes in different colors so you can see it. But hopefully you can imagine I'd end up with this chunk of material, right? In between that green and the blue, I have this solid block. And if I look at a top view, that's what it would look like, right? So this is the block that I'm left with when it's all said and done. It goes from that edge of the hole all the way out to the edge of the board. And if this were 0.5 inches back, where I drew this hole and this board were a 1/4 inch thick, then what I could look at is the area that needs to be sheared. So same idea, we have a force. We said the force was 200 pounds. What's the area that needs to be sheared for failure? It's that green area and what I have drawn in blue. So if I were to write down or calculate that area, what I could say is I have 2 sides. Each side is a 1/4 inch, because that's the depth here of this board, right? Times the distance back. Well, how far back is that? That's that over here, this 0.5 inches. So multiplying all that out, I end up with 0.25 square inches for the total area that must be sheared. So if I were to look at the shear stress on that tear out, I'm still using this V over A, same equation over and over. We're still supporting 200 pounds, but now the area is this 0.25 inches squared, and that gives me 800 pounds per square inch. Now that's if I had a single board, or you can imagine what would happen if I were to think about tear out along here and here. Well, there's the bottom board would have the same thing, right? So I would actually have 4 sides. So depending on what your connection's like, it's just a matter of figuring out how many sides you have for this shear rupture or tear out. So once again, what we talked about today was this idea of shear stress, which is a shear force over area, and it's just a matter of figuring out your forces in your areas. And then with connectors, we could have a lap shear, where you have a single shearing plane, otherwise known as single shear, versus double shear, you have 2 shear planes, and shear rupture or tear out, where I have the block of material coming out with it. Typically that's 2 shear planes as well. So I hope you found that informative, and as usual, let me know if you have any questions or comments. Thanks.